Okay, this is another exam question, and it's a contingency table question, and it makes us think about a couple of things, probability problems and a thing called independence, a test for it. So let's just try. Okay, there's this story. There's a survey concerning holiday preferences with 180 people are chose from. They were asked, do you want to go to the coast? Do you want to visit a game park? Or do you like to stay at home? Okay, well, and it was broken up into males and females. Well, the total number of people, both males and females, adds up to 180. Here's the totals for the people that prefer the coast, game park, or want to stay at home. And here's all the, so we get a total breakdown here. Okay, so now it just says determine the probability that a randomly selected staff is male. Well, we just have to make a fraction here, and the probability of male is a favorable over total. So we have to find the total number of people, the total number of staff, and just divide it by the people that are males, and that's it. The probability of male, there's 83 males in total, divided by 180 staff in total. That's a 46.11% chance on my calculator, and that's it. Now, what about the probability that somebody doesn't want to go to a game park? Well, there's a couple of ways of doing this. I'm going to show you both ways. The people that prefer the coast and the home, if you add them together, you get 118 people out of 180 altogether. That's 65.56%. The total number of staff divided by the people that don't like the game park or would prefer something else, staying at home or the coast. I just added them together. There's another way of doing that. You could actually do it this way. You could figure out the probability that somebody likes a game park, which is 62 over 180. That's 34.44%. Well, the probability of not preferring the game park would be 1 minus that, which would give you exactly the same answer as we got before, 65,56%. Just another way of doing it that makes us think about this, the probability of something happen and the probability of it not happening is just 1 minus it. I like to be able to think about it that way sometimes. Sometimes it's the easy way of figuring out probability problems. Okay, there's another question here. It says, are the events being male and staying at home, are they independent events? Okay, they asked this question, whoa, are the events being male and staying at home independent events? Whenever they say, you're asked about something being independent, write down the test for independence. The probability of A intersection B is the probability of A times the probability of B. That's how we do the test. Okay, the probability of being male, well, that's 83 over 180. We've done that. The probability of staying at home, well, that's easy to figure out. It's 20 out of 180. It's 1 over 9. Well, if they're independent, all we have to do is take those two fractions and multiply them together, the probability of the two separate events, and see if it equals the probability of their intersection. The intersection is the probability of being male and staying at home. Well, that's in the contingency table. Look, 13 people wanted to stay at home and are male, okay? That's an intersection here out of 180. So what we do is we take that fraction, 13 over 180, and we compare it to 83 over 180 times 1 over 9. And our calculators tell us that, A, these two fractions aren't the same. So then we can say, therefore, being male and staying at home are not independent events. And all we do is use this test, work out the probability of the two things separately, and then look in your table. You can find the intersection. Just think about, what does it mean? Male intersection stay at home is where home and male come together right there in the table. That's how I got that 13 out of 180. Okay, well, hopefully that helps with the contingency table questions. And we had to test for independence. Gee, it's so easy if you know how, and pretty hard if you don't know how. Okay.